No, please wait a second. Okay,
Okay.
welcome everybody. This is the very first intercontinental pre-seminar, and we are very happy to have Fredy giving us an introduction to spectral triples, main axioms, and properties. Please.
Okay. Thank you. Thank you for the invitation. Let me know if you can hear me well, because maybe I will have some problems with the connection. I hope no. So okay. So today I want to talk about a brief introduction to spectral triples. So I want to be very basic, actually, because so I was told that this will be an introduction talk about for another talk about spectral triples. So what I want to do is uh, give some the more important notions in the non-commutative geometry, non-commutative spin geometry, so which was created by Cons. Okay, so I don't know how to. Okay, so my talk is will consist of three steps: classical motivations, definition, and axioms. If time permits, so I will give one example. So okay. So what is the what is the big story about this philosophy of the non-commutative geometry? So this story begins with the Heffan duality. So as many of you know, so in the theory of C-star algebras, we have this theorem, which is called Heffan-Naimark. So I didn't write Heffan-Naimark, okay, but this is called Heffan-Naimark, which gives a correspondence between locally compact Hausdorff spaces and C-star algebras. So this in this duality, the locally compact this map C in this diagram, this which is a contour, from the locally compact Hausdorff spaces to the C-star algebras. And from C-star algebras, we can go back to the locally compact Hausdorff spaces by this functor omega, which is given by the topological space of star morphisms from my sister algebra to C, which is equipped with the weak star topology. So from this duality, we can give actually a big dictionary, which gives a correspondence of concepts of topological spaces and objects and notions in C-star algebras. So, for example, isomorphisms, or homeomorphisms of topological spaces corresponds to star isomorphisms of C-star algebras, and uh, and open sets corresponds to closed ideals in the sister algebra and so on. But okay, we have this duality. So now the question is if we have some if we have a analogous dual object corresponding to topological spaces with more structure. For example, Riemannian manifolds. So what is what are the corresponding objects? What are the objects? What are the dual objects corresponding to Riemannian manifolds? So in this talk, we will focus only in the Riemannian spin manifolds. So for the corresponding objects, the corresponding dual objects to Riemannian spin manifolds are called the spectral ripples. So which spectral ripples. So here we have actually I wrote 4 letters. So, but in principle, we have a spectral ripple consists of a star algebra, a Hilbert space, and a Dirac operator. So, what is a spin manifold? So, spin manifolds are very I don't know how to say important important manifolds in the differential geometry, where it is possible to construct principal bundles having the spin groups as structure groups, or which is or equivalently if it's second Stiglitz class vanished. So why are these Riemannian spin manifolds so important? Because we can construct the Dirac operators, and the geometry of these manifolds are encoded by the properties of the Dirac operator. So this is the famous Kant's reconstruction theorem, which says that from a commutative spectral triple we can construct a corresponding Riemannian spin manifold where the algebra A is the same infinity functions, the smooth functions of the space. So here I wrote the seminal papers of Kant, where he did this where he gave this reconstruction theorem. So actually, which was surprised for me was that this problem was initially formulated in 1996, and he solved the problem until 2013. So okay, so now I want to give the precise definition of okay, as I already said before, for the spin manifold, we have the canonical spectral ripple, where A is the same infinity, the smooth functions of the manifolds. The Hilbert space is the Hilbert space of square integral sections of the spinor bundle, where the inner product is defined by the integral of functions by using a measure induced by the metric of the manifold of there is a long story. So, and the action is just given by multiplication of sections. So, and the Dirac operator is the operator the Dirac operator associated to the Levi-Civita connection of the metric. And it turns out that this Dirac operator admits self-adjoint extension. So in principle, it's symmetric, but admits self-adjoint extensions where with the compact resolvent property. So, which means that this the spectrum of which is equivalent to say that the spectrum of the Dirac operator is discrete and goes to infinity. So, okay, in okay, here I have the Dirac operator of the two sphere, which is given by the Levi-Civita connection and which is defined in this way. So in the classical geometry, we have this canonical spectral triple. But for you, I have a more basic example. So a more basic example is S1. So if we take if we take a S1 as a space, so an A, the infinity functions of S1, and the Hilbert space are the Hilbert space of L2 functions of S1, and D just defined in this way is just the derivation. So with this minus I, so the complex number. So this minus I we need it in order to have separate joins of the Dirac operator. So in this case, the inner product is the usual inner product in the L2 functions. And in this case, we have that the commutator is given just by the multiplications by the derivative of f, and we have that for this case it's not difficult to see that this symmetric with respect to this inner product and admits self-adjoint extensions to the Hilbert space. So, and the eigenvectors and the eigenvalues are given by these functions and these numbers. So, as I said before, the spectrum of the Dirac operator is discrete, and in this case goes to infinity. So, the absolute value of these numbers. So implying that the compact resolver is compact. So now I have to go to the precise definition. So what is a spectral triple? A spectral triple or unbounded K cycle consists of three objects: star algebra, unital star algebra, a Hilbert space, and a self-adjoint operator acting on this Hilbert space. So this star algebra should be as dense star algebra of C star algebra A. So So in principle, we have these three elements, these three objects. So in many cases, we have that, or in many examples in the literature, we have that this A is actually a pre-sister algebra. What does this mean? It means that the inclusion is continuous and A is stable under the holomorphic functional calculus. So as you see, this is a very strong condition of this in this star algebra. But in many examples, we have that this star algebra A will be a pre-shed pre-star algebra actually. So, and we have we have two more objects, gamma, which is a self-adjoint unitary operator. So in the classical geometry, in the theory of the Dirac operators of spin Riemannian geometry, we have we have the existence of these two objects. The gamma, which induce a sec2 grading in the Hilbert space, and J, which is an antilinear isometry, which is related to the with a real structure. So okay, as I said before, this gamma induces a sec2 grading. I mean the gamma must satisfies these two conditions that commutes with the representation, which is given by this equation, and anticommutes with the Dirac operator. So in the sec2 grading, we have that in this case the representation and the Dirac operator look like this 2 times 2 matrices. So, and here which is important to say that D plus minus in these two operators, D plus, D minus and D plus, just change the Hilbert spaces in this sec2 gradient. So so what are the conditions for the real structure? For the real structure, so we have that the g squared should be plus minus 1 plus minus the identity. This J has to commute or anti-commute with the Dirac operator, and the same with the sector gradient gamma. So why is it very important, this real structure? So it is important because this J allows us to construct a representation of the opposite algebra A. So that's what I mean by anti-representation of A. So and this and these two representations, p and p opposite, pi and pi opposite, should commute. So, and when A is commutative, we also require that the representation should satisfy this equation. So maybe in this talk we will not need this last condition, but okay. So the most important thing in this slide that the real structure induces an anti-representation of the algebra. So now we are ready to talk about the axioms that a spectral triple must hold. So the first option is the dimension. So in the classical case, this option is related to the dimension of the Riemannian manifold. So this option says there is an integer, the metric dimension of the spectral triple, such that this operator, the absolute value, the inverse of the absolute value of the Dirac operator, is an infinitesimal of order one over n. So, or equivalently, the absolute value minus n with power minus n is an infinitesimal of order one of order one. So what is an infinitesimal? So for an infinitesimal for alpha in the real numbers, in the positive real numbers, an infinitesimal of order alpha is an operator, are the operators which satisfies this the where give have to this how to say which the characteristic values of the Dirac operator are dominated por these numbers. So this integer in the classical case coincides with the for the canonical spectral triple. We have that this integer is actually the dimension of the Riemannian manifold. So, and this allows us to define a non-commutative integral. So there is also a big story about this non-commutative integral. So where the Dixmuir trace is involved, and so which by question of time I'm not going to say about this story. But for example, for the S2, or maybe we can think of S1, for S2, the spectrum of the Dirac operator is given by these numbers, and in this case, we can see that for this case the dimension is actually 2. So, and what about 0? So, 0, I don't know very well how to say the metric dimension. So, but maybe I will skip this question for the moment because of time. So, how much time do I have? Maybe I will go faster.
More minutes.
Sorry?
You have like 10 more minutes.
10 more minutes. Okay. So maybe I will skip some slides. So axiom 2. So what does axiom 2 say? So for the axiom 2 the axiom 2 says that for all A, B, and A, the following commutation relations holds. So what in this case, what is this saying? This is saying that how did I say? The representation of the opposite algebra commutes with the commutators. So, in the classical case, this condition expresses the fact that the Dirac operator is actually a first order differential operator. So, and in the no commutative setting, this allows us to define representations of this algebra, A tensor A op, which is very important to define Hochschild homology and to talk about the orientation axiom. So, okay. The axiom 3, the regularity, the regularity says that the commutators and says that for all for every element in our algebra, these elements and the commutator with the Dirac operator belongs to the domain of smoothness. So, or domain of smoothness of this delta k. So in the commutative case, what does this mean? It means that this algebra is inside the infinity function of the manifold. So in the no commutative setting, this domain of smoothness can be considered as the smooth operators. So, and these conditions allows us to define a locally convex topology on A given by these seminors. And this axiom, this regularity axiom, actually implies that the underlying algebra, I mean A, this is actually a pre-sister algebra. So as I said before at the beginning of this talk, when if we have this regularity, if this regularity axiom holds, so we actually have our algebra is a pre-sister algebra, a Frechet pre-sister algebra. So the orientability, so the axiom 4 is about the orientability. In the classical case, this is related to the existence of a volume form of our spin manifold. All the spin manifolds are orientable. So there is a volume form. So, and the orientability condition says that there is a Hochschild cycle. I mean, there is a cycle, a cycle in this complex, Hochschild complex C, in this Hochschild complex where the boundary is defined in this way. So the orientability condition says that this Hochschild we should have a Hochschild cycle. So, and this Hochschild cycle gives volume analogous, no commutative analogous of a volume form for our no commutative manifold. So the finiteness is about the property is about the property of that the smooth vectors, the in the classical case, this H infinity, this H infinity, which is the intersection of this term of decay of decay in the classical if the classical setting, we have that this H infinity corresponds to the module of smooth sections of the vector bundle on which the Dirac operator acts. So this finiteness condition says that this space of this A module should be a projective, finitely generated projective left aid module. So with the Hermitian pairing, which has to satisfy this condition. So this option is saying that this space H infinity is the analogous of the module of a smooth section of the vector bundle. So, but here this property, this is the most important property, that this module have to be finite projective module. So, and we can forget at the moment we can forget the condition of the Hermitian pairing. So, in this case, we have that H infinity is actually a pre-Hilbert module. When we have if we have finiteness, we can we get that this H infinity is actually a pre-Hilbert module. So okay, and then here is the non-commutative integral. So here is the non-commutative integral is involved in this equation. So there is also a big story about this non-commutative integral, and there is also a long discussion about this definition of this Hermitian pairing, but by question of time, we cannot talk about it. So, and finally, we have the last option, last axiom, the Poincare duality. So, in the classical case, this condition, this theorem is a theorem actually in topology. Classically, this is formulated as a knot generated by linear pairing on the cohomology ring of our manifold. So this is saying that this pairing given by this which is defined in this way is actually not non-degenerate. So, what is the transition to the non-commutative setting? So, the transition is the reason is that there is a relation between the K theory of the manifold and these homology rings. So I think the there is an isomorphism. No, it's not isomorphism. There is I forgot the relation, but there is a relation between these two objects, the K theory and this and this cohomology ring, and that's why we can formulate this Poincare duality condition, this Poincare duality in the non-commutative setting by using the K theory. So and here is where the the representation pi and the anti-representation pi opposite are play an important role. So in this case, we have that the pairing is given by this is given by the index of a Fredholm operator. So
Sorry,
which is
Fredy, we are running a bit out of time, so if you could wrap it up in the next minute, this would be great. Thank you.
Yeah. Okay. So I think we have two more slides. I think this is the last. So, and in this case, okay, in this at least this last option, there is also a long story. So, so the most important thing for me is that this operator is Fredholm. So this HM and this DDM, this HM are some of copies of the Hilbert space, and this the DM is a sum of copies of the Dirac operator. So finally, we have this table with the signs that the real that our operator has to satisfy. So, but okay, there is a reason for these conditions of these signs of these commutation relations. So, and these signs has to do with the periodicity of the real K theory. So, but okay, which is something I don't know very well. So, but we know that there is a classical reason. So, at the end, so I have some examples, but I don't have much time, so I will skip this, which is a non-commutative torus. Perhaps many of you know this example very well, but I will skip. So, and that's it. That I
Okay.
want. That's
Thank
all
you,
I want.
Fredy. Thanks a lot. So, are there questions?
Fredy, thanks for the nice talk. Could you say something about examples on quantum groups?
Quantum groups. Yes. Yes. We know there are many examples for quantum groups, but I didn't write any of them. So, but the examples of the quantum groups, I think one of the most important examples is the spectral ripple for the Podlesh sphere of Dabrowski sitters, and the spectral ripple for the SU2, quantum SU2.
And
Yeah,
maybe for the B series flag manifold constructed by yourself. Also, the B series flag manifold, I guess the example that you constructed.
Yes, but we don't have, so okay, we only have some conditions, but I mean only yes, I constructed one example for the top list torus. Okay, but in my example for the top list torus, we get all the conditions accept the Poincare duality and what is this? First order. So in the first order condition, so the first order condition has been a problem in the examples of spectral triples for the quantum groups, because this condition has to be modified. I mean, these commutators should be compact, as far as I know. So for the quantum groups, we don't have first order condition. We have first order conditions up to compact operators, not zero.
Right. Thank you.
Yeah.
Maybe a small technical question. So in axiom 6, I guess, was it there?
Yeah, Poincare duality.
Oh yeah, you speak of the K-theory ring of this algebra, A tensor A opposite. But then usually for C-star algebra, K-theory is just a group, right? So where does the ring structure come from in this case?
Yeah. Okay. In this case, we actually we can define a K-theory in the same way we do for the C-star algebras, but for the Frechet pre-C-star algebras. So actually we can there is the construction is the same but there are I think there are many subtleties in the definition, but the definitions is the definitions are the same. You know, for example, the K0 is you define the Murray-Neumann equivalence between projections and you have a semigroup and you
Right. But
yeah.
so my question is, so if you do this for C-star algebra, you just get a group, right? K0 is just a group. You don't have a ring structure usually. So I'm wondering why in this case it's a ring, like it says.
No. In this case, K0 is also a group.
Oh, okay.
As I said, the same definitions we have for the C-star algebras of this K0, K1 works for the Frechet pre-C-star algebras.
Okay, thank you.
Okay, so if there are no more questions, let's thank Fredy again. Thanks a lot for the nice talk.
Thank you.
And now there's